Right, graphs with asymptotes. Now, other than the very basic one, y equals 1 on x, standard hyperbola sort of thing, you don't really see too many graphs with asymptotes in 2-net. Probably more in 3-net. And the ones we're sort of really interested in are the ones involving polynomials on polynomials. Keep that in mind. Curves will always bend towards the asymptotes. They never touch them, of course, because it's like a limit. Right? But it is possible for curves to cut the asymptotes. So often people go, no, you can't touch them. You can touch them. But it's the specific type of ones that you can. Right? Vertical ones you can never touch, because a vertical asymptote is simply saying this is not in the domain. So if it's not in the domain, it'll never touch that asymptote. Okay? It's the oblique ones or the horizontal ones that you can cut, because oblique and horizontal asymptotes are simply telling you what happens to the curve out of the extremities. What is like its limit? What's it going to? So when it's not near infinity, and not near infinity is pretty much every number you can think of. Right? 1,000,000 is not near infinity. Any number is not near infinity. Even infinity minus 1, if you could possibly calculate that, is not near infinity. But we use this basic idea when we want to have a look at the equation to work out the picture. If you've got a polynomial over a polynomial, then remember your polynomial division. You could always rewrite that as quotient plus remainder over the divisor. And when it's in that form, you can tell an awful lot about what the curve looks like. The bottom of the fraction. Bottom of the fraction can never equal 0. We know that. It's a basic rule. That tells us our vertical asymptotes. The quotient is the oblique or the horizontal asymptote. But then it's the top, it's the numerator, which tells us if we are going to cut it or not. If you can solve the top of that fraction equals 0, then it will cut the oblique or the horizontal asymptote at that value. Okay. And that, as I say, is probably the biggest misconception there are about asymptotes, that it can't cut them, and it can. The oblique or the horizontal ones are just saying what happens out of the extremities. It's like it doesn't exist anywhere else, so it can cut it. So let's have a look at one. X plus 3, x minus 2, x minus 1, x plus 1, which is a quadratic on a quadratic. If I was to do the polynomial division, if I didn't see it straight away, well, x squared and x squared is 1. My remainder becomes x minus 5, so it has an oblique asymptote. There's my equation. So I can read off that information. X-intercepts, well, I'll go to the original equation for that. X-intercepts will be minus 3 and 2. Plot those in. Y-intercept is 6. Plot that in. Vertical asymptotes are plus or minus 1. I'll draw those. Horizontal asymptote at 1. Draw that in. Now, it is possible for the top of that fraction to equal 0. So at 5, it will cut that horizontal asymptote. Okay. We should be able to fill in from here, because the curve has to bend towards the asymptotes. The only place it cuts that horizontal one is at 5. So in between these two, I must have a concave up shape, because it can't come down. Because if it came down, it would have to cut the horizontal one, but I know it doesn't. So it must bend upwards there. I know it goes through minus 3. It's got to bend towards these two asymptotes and never cut it, so I must have that hyperbolic shape. The right-hand side is the interesting one, because it must go towards the asymptote, cuts through 2, cuts through 5, but then at somewhere it must turn and come back down so it can bend towards the asymptote. So there's our left-hand bit. There's our middle bit. And there's my very dodgy right-hand bit. I didn't really have enough room to fit it in. But somewhere it must, because like it's going to cut the horizontal, it's going to go up and go up, but at some point, because it's got to come back and bend towards that asymptote. So it must come down and inflect and go towards that asymptote. And so there's our sketch, all from just looking at the equation of the curve. We got that information. All right, we'll do another one. Here we go. That polynomial division ends up being, let's work it out. There we go, x minus 1. My remainder is 4x minus 4. So I have an oblique asymptote this time, x minus 1. Let's draw it all in. I got 3 x-intercepts. Y-intercept is at minus a third. Vertical asymptotes at minus 2 and positive 3. Draw them in. We have an oblique asymptote. Y equals x minus 1. Draw it in. Straight away I know it cuts it because look, it goes through the x-intercept we've already identified. Okay, got to bend towards the asymptotes. So, on the left-hand side, I'm either going to be trapped in this little triangle here, or I'll go like a hyperbola. Well, I know I'm not going to go like the hyperbola because I don't have an x-intercept. Got to be trapped in the little triangle there. Same on the right-hand side. I've got to be trapped in the triangle at the top. In between the two vertical ones is the interesting bit. But I know I've got to go through minus a third in this point. So it looks like I'm coming down from the asymptote. So I can go through the point, turn, then I'll probably turn again and go down towards the asymptote. So let's draw it. There's the little triangle. Whee! There's our graph. Okay? All right. Used to be a fast network, but has been superseded.